Okay, we're continuing with question 3 of the 2015 free response. Question 3 is a rotations question. As I've said, usually question 3 or question 2 is going to deal with rotations. Also, the rotation question tends to be the trickier one. It could either be really easy or really tricky. This one is probably closer to the tricky side, mostly because of the fact that we haven't done a problem like this before. Now, if we look at part A, it says right in the beginning that we're going to be using integral calculus, and it wants for the rotational inertia of the rod around, and thankfully they actually tell us what the answer should end up being. Now this is nice because we know what the answer should be, so it's a way for us to check our answer. Now if you look on the reference table, you'll see this equation for the rotational inertia. The rotational inertia is equal to the integral of r squared dm. So that means that we have to integrate r squared with respect to the mass. Now, this is where it gets tricky, and it's why we're going over this. You need to see how changing the radius affects the mass. Now, you look, if this object is of uniform density, an object of this length has a different mass than an object of that length. So we have to use an equation that you haven't seen before, and it looks like this. So this is what's called the mass per unit length, or the linear mass density. Basically, it's like density, except only in the case of talking about the length of an object rather than the volume of the object. All right, so I can rewrite this as, for solving for mass, lambda L. Now, the thing is, I need to know dm. So, if I change the mass of the object, the linear massity stays the same, and I end up getting this relationship. So this tells me how I can replace the dm with a dl instead, because I need, in order for me to actually integrate this, I need to change this dm right here, because it's not going to work integrating r, because r actually does change as I change the length. So I replace the dm with lambda dl. The lambda is constant, so I'm pulling it out of the integral. I'm also going to replace the r with the length, because that's what the length is. And I also have to make sure that I set my bounds. My bounds for my integral, well, I'm going to start at 0 at the pivot, and I want to get to the full length L, like this. So the integral of L squared is 1/3 L cubed, and I have to set it between 0 and L. So then this equals lambda times 1/3 L cubed minus 1/3 0 cubed, which is just equal to lambda 1/3 L cubed. All right. Unfortunately, L's not a given lambda's not a given term. So I have to replace lambda with this m over L. So now I get this. M over L times 1/3 of L squared, L cubed. This L crosses out with one of those L's. And look what we have here. 1/2 ml squared. So here I've shown, using integral calculus, how the rotational inertia, that's a 3, how the rotational inertia for a rod rotating around a pivot at its end is 1/3 ml squared. For this part, they want to know about the velocity of the free end of the rod. So what they want to know is what's the velocity here, and in particular they're looking for the linear velocity. Now, in order for me to actually figure out the linear velocity, I first need to figure out what the rotational velocity of the rod's going to be, and then I can find the linear from that. Now, the rod starts at some height and then falls to its lowest point. I know it has some potential here, and then it ends up turning into rotational kinetic down here. So I can actually use conservation of energy to see what the rotational velocity would be. So UG equals K, all right? You might want to have to say that energy is conserved. Energy conserved. So then we have mgh equals 1/2 I omega squared. So it ends up being mg. Now here's the thing. The potential energy is of the center of mass. So the center of mass is right in the middle. They actually give you this line. So the height at which the center of mass changes goes from being up here to actually being L divided by 2. So it doesn't actually fall the full length of the rod. It only falls half the length of the rod. 1/2, and the rotational inertia from before is still 1/3 ml squared omega squared. All right, so one of these L's crosses out with this L. These masses cross out like normal. This half crosses out with that half. And so what I end up getting is that omega squared equals 3g over L. Or that omega equals square root of 3g over L. Now, in order to find the linear speed, I use this relationship, that the linear speed equals omega r, and I'm trying to find the linear speed of the very end. So what I end up doing is I have to multiply the length between the pivot and the very end, which is L. So the linear speed at the very end is equal to L times the square root of 3g over L. And to simplify this a bit, 3gl squared over L. This L crosses out with one of those L's. End up getting that the linear speed should be equal to the square root of 3gl. And there we go. And this was a 4-point question. There was 1 point for realizing that you had to deal with conservation of energy. So this was 1 point. You had 1 point for realizing this, substitution. 1 point for realizing that the height change was half. And then 1 point for using this, V equals omega r. Doing all those, you get 1 point. So part C is something that you guys should be aware of and should know what you're expected to do just from looking at this. So they have a chart, and in the chart there are 2 blank spots. What this means is what we're going to end up having to do is we're going to have to take one of these, or both, who knows, and we have to change it some way so that when we graph this data, we'll get a linear line. That's our goal, is to find a linear line. Now, I'm going to pull up that equation that we just found, that V equals the square root of 3g over L. Now, looking at this, we can see that there's a linear relationship between velocity and root L, or V squared and L. So it wants us to figure out how to find a straight line where the slope can be used to find gravity. Now, if I do either of these graphs, I will end up getting a straight line that can be used to find gravity. If I do this first one, what I will end up getting, rewriting it like this, is that this section right here, the root 3g, is going to equal my slope. On the other hand, if I use this relationship, I get rewritten looking like this, and in this case, this will equal my slope. So either way, I'm going to get the same answer. The only difference is that whether my slope is going to be equal to 3g or rad 3g. But we'll deal with that in the next section. So you have to choose for which what to put for the horizontal and vertical axis, whether we want to do v and rad L or v squared and L. It's really up to you. So what I'm going to do is I'm going to say that the horizontal the horizontal axis is square root of L. And I'm going to say that the vertical axis is v, the velocity. Velocity. Now, another part that's actually important to note is here. It says use the remaining rows of the table above to record the quantities. So we have to label the row and include the units. Velocity is already there. Instead, I have to include rad L. So then I have to just put in the actual values for this. Root 0.5, rad 0.75, and so on and so on. And this earns you 1 point for realizing that these two have to be graphed to get a linear line. Part D is pretty straightforward. We just take these two numbers and graph them onto, or two data points, graph them on here. So looking at this, we can see that we could probably go up by factors of 0.25, 0.5, 1, 1.25, 1.5, 1.75. And for velocity, on the side, it'll go, we actually can skip lines, so we can actually start down here at 3, and then go up to 5, 4, 5, 6, 7, and 8. I apologize that I'm not up on the edges, but right now I cannot get to them. Don't forget, you have to label your axes, including the units as well. I'm not doing it right now, but you have to. Again, go through and plot all these values. I'm just going to do this really quick. So this point starts right there. This one goes up to around here-ish. This one is probably somewhere around here. I'm just eyeballing it right now, not really going too far along. To 122. All the way up to here. And this one's probably right there. All right. And then it says draw a straight line through the points. Remember, you want to make sure that you're reading the directions to see exactly what you're expected to do. So draw a line, boom, there you go. All right, so this one is worth 3 points. You got 1 point for labeling your axes and creating a scale so that we get a majority of the points filling up at least half of the grid. You get 1 point for plotting values that correlate to what you put into the chart, which is definitely something that you want to remember, that the chart, whatever you put in this chart, if you put it into the graph, you get some of those points. And then drawing a straight line, you get another point for that. All right. So this was 3 points, and for the most part, this should have been the easiest 3 points to get. All right, the last part, part E. Now we're going to take what we just did, our line, and we're going to determine G. Remember, when I'm using this relation, the velocity is proportional to square root of L. We had this equation, root 3g root L. This is my y. This is my x. So that means that this is my slope. So my slope of the line is going to equal to rad 3g. Just take a few points. I could take that point, and let's see. I guess this point. Why not? Oh yeah, when you do slope, you want to make sure that the points are as far away as possible. So that ends up being 7 minus 2 over, I believe this is 1.35 minus 0.35, 5 over 1. So the slope is 5, and that means that 5 equals rad 3g. That we get that g should equal 25 divided by 3, whatever that is. Square both sides. And then that's your answer. And then for the second part, it says describe 2 ways in which the effects of air resistance can be reduced. There's a few different ways. Basically, you want to try and make it aerodynamical. Dynamic. By maybe turning it into some sort of blade-like object. You can make it heavier. You can do it, one of the easiest ways definitely to get rid of air resistance is also to do it in a vacuum or in space. And then another one, again, because you want to try and limit how much this rod is interacting with the air, you can make the rod shorter. The one reason why we want a heavier rod, just explain that one. Heavier rod would make it so that the frictional force, the drag force, doesn't affect the speed as much. All right, so as far as points go, this one was 2 points, basically saying one of those, or two of these things, 2 of those 4 things. There are probably other examples, but those are the 2 easier ones to see. And then for the first part, you ended up getting, this one was also worth 2 points, and you basically got 1 point for getting the slope. So this one was worth 1 point to get this entire slope, and then 1 point for correctly realizing that the slope was equal to rad 3g, or whatever you did previously. Remember, if you instead did v squared and L, then your slope would actually just be equal to 3g rather than rad 3g. So again, whatever you did, that's what's up. All right.